In this video, let's go ahead and check our understanding of factors, multiples, and rational expressions together. Now, to get the most out of this video, I encourage you to grab some paper, something to write with, and let's do some math together. For these first two questions, we're going to go ahead and write the prime factorization for each number. Then we're going to go ahead and write the total number of factors the number is going to have, and then write a complete factor list. All right, so let's see. For number one, we have the number 528. So let's see what we can do and break this down into. So what do we know we can divide 528 by? Well, it's an even number, right? So we can just go ahead and divide it by 2. You could use other numbers as well if you know some other divisibility rules. But I'm just going to start with this 2 here. Now, half of 500 is going to be 250, and half of 28 is 14. So 250 plus 14 is going to be 264. So I'm going to write 264 here. All right. And now this 2 is prime over here, so we can go ahead and stop with that one. But the 264 can definitely be broken down, right? Let's see, 264 is also an even number, so I'm going to put a 2 here. And then let's see, half of 200 is 100, half of 64 is 32. So we're looking at 132. All right, this 2 over here again is prime. This 132, you could divide it by a 2 or 3. I'm going to go with 2 here again though, just because I'm going to stick with my even numbers here. So 2 times half of 100 is 50, half of 32 is 16. 50 plus 16 is going to be 66. So I'm going to put a 66 here. Now dividing 66 down, I'm going to use 2 again, just stay on that trend over here. So 33 and 2. This 33 can break down into what, 3 and 11. All right, so at this point, I think I have all prime numbers. So if we're going to go ahead and write the prime factorization, we can just go ahead and say that it's going to be equal to 2 to the what? 2 to the 4th power. Looks like there's 4 2's multiplied together, multiplied by 3, multiplied by 11. Now, as for the number of factors, what you can do here is, once you have this written in this exponential form for the prime factorization, keep in mind that there's 1 as an exponent for each of these. But if you add 1 to this 4, you get 5. If you add 1 to this 1, you get 2. If you add this 1, you get 2. So 5 times 2 is 10. 10 times 2 is 20. So we're going to have a total of 20 factors for this number, 528. All right, now let's see, what are these factors going to be? Well, we should start by looking for 20 in total, or 10 pairs. We should start with 1 and 528. That takes care of 2 of them, but we need 9 more rows over here. If you look at our factor tree list here, we do see 2 on the list, so 2 is definitely going to be on there. We also see a 3 on the list. I'm going to put a 3 over there. You don't see a 4, however, because it's composite, but you can see 2 2's do make a 4, so we can put a 4 on the list here. There's no 5 on the list. 5's prime would be there. You don't see a 6 because it's composite, but 3 times 2 does get you 6. So let's see here. That's going to take care of half the pairs. There's no 7 because 7's prime. What about 8? Well, 8 comes from 2 times 2 times 2, right? So 8's going to definitely be on the list here. There's no 9 because you would have to have 2 3s. We only have 1 3. There's no 10. 10 needs 5. 11. 11's definitely on the list here, so we can put 11 right over here. What about 12? 12 comes from what? 2 times 2 times 3. That's 12, right? So we can go ahead and put a 12 on the list here. And at a certain point, we just got to make sure we have all the ones we need. So 1, 2, 3, 4, 5, 6, 7, 8. We're looking for 2 more rows here. So let's see, we need 2 more rows. After 12, we have what? 13. Let's see, 13's prime wouldn't be on there. What about 14? We need a 7. 15, no. 16, let's see here, 2, 2, 2, and 2, that makes 16, so 16 is definitely on the list. What about 17? That's prime. 18, I don't think we can do. 19's prime. 20 needs 5. 21, nope. 22, oh, I think we have 22 here, right? Just because 11 times 2 would be 22. And then you can go ahead and stop right here, just because I think we have 10 rows going across here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we should have everything. Now what goes with the 2? It's definitely going to be 264. So let's go ahead and put that right over here. What goes with the 3? Well, 3 you can see right over here. So what's 11 times 2? That's 22 times 2 is 44, times 2 is 88, times 2 is going to be 176. So it's going to be 3 times 176. All right, what goes with this 4 here? Well, 4 comes from this 2 and the 2, right? So let's see what the rest of the numbers are going to multiply to get. 2 times 2 is going to be 4. 4 times 3 is 12. 12 times 11 is 132. So we're going to do 4 times 132. That'll get us to 528. All right, for the 6 here, 6 comes from this 2 and 3 multiplied together. So let's see, 11 times 2 is 22, that's 44, that's 88. So we're looking at 6 times 88. For the 8 here, 8 comes from the 2, the 2, and the 2. So just multiply the rest of these. So this is going to be 6 times 11 is 66. So it's 8 times 66. That gets us 528. For 11, that comes from right over here. So that's 11. What about the rest of these numbers? 3 times 2 is 6. That's 12. That's 24. That's 48. So 11 times 48 gets us this 528. For 12, 12 looks like we have a 2, 2, and a 3. These will get us 12. So the rest of these will be what? 11 times this 4 is 44. So 12 times 44 should get us that 528. Now for the 16 that we see here, 16 comes from 2, 2, 2, and 2. So the rest of these just makes 33. So that means 16 times 33 is going to be that 528. And then for this 22 at the end here, 22 comes from this 11 and 2. So what does the rest of these get you? So this is going to be 4, 8, and then 24. So it's 22 times 24 also gets us this 528. So here are all our factors. All right, let's take a look at number 2, where we have the number 630. Let's go ahead and try this process again. If you feel like you got the hang of it now, feel free to pause and again, try it on your own. Let's see here, 630. I think a nice number to kind of start here with here is going to be a 10 and 63. They're both composite here, so I'm just going to go ahead and break the 10 up into 5 and 2. These are both prime numbers, so I'm just going to go ahead and stop there with those. For 63, I'm going to go with a 7 and 9 here. The 7 here is definitely prime, but 9 is composite. Then 9 is going to break up here into 3 times 3. All right, so these help us get all our little prime factors of 630. All right, so for the prime factorization for 630, looks like we have 1, 2. I'm going to put 2 to the first power. Looks like there are 2 3s, so times 3 to the second power, times, it looks like there's 1 5 and 1 7. So this would be our prime factorization for 630. All right, now to determine the number of factors, let's just go ahead and add 1 to each of these exponents. So this would be 2, this would be 3, this would be 2, this would be 2. All right, so 2 times 3 is going to be 6. 6 times 2 is going to be 12. 12 times 2 is going to be 24. So we're looking for 24 factors here for the number 630. If we're looking for 24 factors, that means we need to have 12 pairs here. So let's see, we're going to start off with 1 and 630. So that one's a given. There's going to be a 2 on the list because I see a 2 on the list of prime factors. There's also going to be a 3 on that list. We see a 3. We need 2 2s to make 4, so we can't do that, but we can do 5. 6 we can do just because there's a 2 and a 3. Let's see, so we're going to put the 6. We can also do 7, right, just because there's a 7 on the list. Can we do 8? I don't think we can do 8 here. We need 3 2s. Can we do 9? We can definitely do 9 just because there's 2 3s on the list. Can we do 10? Yes, because there's a 5 and a 2 on the list. 11, I don't think we can do 11. 12, I think 12's out. 13's out. 14, 14 is in. We have a 7 and a 2. That makes 14. 15 is also in because we have a 5 and a 3. Let's see, 16, no, 17, no, 18. I think we have 18 on here actually, right? 18 comes from 3, 3, and 2. 19, no, and 20, no. 21, I think 21 is we're going to go with because we have a 7 and a 3. And then if you're wondering if we should keep looking, we should stop here because, again, we're looking for 24 factors here. We have 1, 2, 3, 4, 5, 6 pairs, 7, 8, 9, 10, 11, 12 pairs. 12 pairs is 24 factors. All right, so let's go ahead and just do some multiplication now. So we see this 2 here, that's right over here. 2 times what is 630? Let's see here, we have 5 times 7 is 35. 35, and then we have what, 35 times 3 times 3. I believe that should be 315, right? So that's also half of 630, so hopefully that makes sense. Then for this 3 over here, that's right over on this spot here. So let's go ahead and multiply the rest of these. 5 times 2 is going to be 10. That's going to be 70. That's going to be 210. So 3 times 210 is 630. For 5 here, that's right over here. Let's see if we multiply the rest of these. So this is going to be 9, right? 9 times 7 is going to be 63. 63 times 2 is going to be 126. So I think it's going to be 5 times this 126. For 6, 6 is going to come from 3 and 2. So the rest of these, let's see, it's going to be 5 times 3 is 15, times 7 is going to be 105. For the 7 over here, 7's right here. So let's see, 5 times 2 is 10. 10 times 9 is going to be 90. So 7 times 90 is 630. Hopefully that makes sense. This 9 over here comes from 3 and 3, so that's 9. 9 times over here is going to be 70, so it's 9 times 70. Then this 10 is coming from the 5 and 2. So if we multiply 7, 3 and 3, we should be getting 63. That's what we started with our tree, so hopefully that makes sense. 14 here is coming from 2 and 7. That's going to be 14. So what's the rest of these? So it's 9 times 5. So it's like 14 times 45 is going to be that 630. For 15, 15 is coming from 5 and 3, right? So the rest of these, let's see, that's 3 times 2 is 6. 6 times 7 is 42. Looks like 15 times 42 would be 630 as well. For 18, 18 is going to be what? 3 times 3 is 9 times 2. That's 18. So it looks like 5 times 7, that's going to be 35 here. Okay. For 21, 21, we are knowing that's coming from 7 and 3. That's 21. So 5 times 2 is 10 times 3. That's going to be 30. So these would be our 24 factors for 630. All right, moving on to number 3 and 4. Let's go ahead and just factor each of these monomials and then write 5 unique factors. There's going to be a lot of factors for these, but we're just going to write 5. So just make sure you know if it goes into it evenly or not, or will multiply to go into the original monomial. So if we're going to write this as a factored version here, 24, I'm not going to write out the tree for it because it's a smaller number here, but 24 breaks into 2 times 2 times 2 times 3. And then the variable parts are actually a little bit more straightforward. There's going to be 4 of these a's multiplied together, and then there are 3 of these b's multiplied together. So this would be the factored version for this monomial. All right, and then if you're going to go ahead and write some unique factors, there's so many that you could actually choose from here, but let me just write maybe 5 that I think would be good to just test out here. You could say something like 12AB, right? That's definitely going to go into it. So again, any combination of any of these individual factors is going to get you there. So you could also say something like, I don't know, 2a squared b. Just don't go over the exponents in terms of what we actually have. They have to be smaller or equal to those exponents, so we can write that. You could also say something like 3b cubed. You don't have to use both letters. You can just use one of them, so that's an option here. You could also say something just like 1, right? 1 goes into every monomial or any value, so that could be a factor as well. And then you could also, I don't know, just, you could say the entire thing itself. You could say 24a to the 4th b cubed, but maybe I'll just go ahead and say something like a to the 4th power because that definitely goes into the entire monomial. So those are just 5 options. I'm going to put ... here just so you know. There's definitely way more of these, but these are just 5 possible factors. Okay. For number 4, we have 56 x cubed y z to the 2nd power. So for 56, I think that's what, 2 times 28, and 28 breaks into 2 and 14. 14 is 2 and 7. So you can check that and multiply it out. It's really 8 times 7, and 8 breaks into 2, 2, 2. There are 3 x's being multiplied together here. There's 1 y being multiplied here, and there are 2 z's being multiplied. So this would be the factored monomial, right? If you just kind of expand it. And if you want to write some possible factors here, let me see if I can do anything different than before, but you could just say y, right? There's definitely a y on the list over there. You could also say something just like yz, right? That's a combination here. I'm going to say something like, I don't know, I'll say 14x, right? I just did 2 times 7 times one of the x's. You could also say something like 56 x. Again, you can use the entire whole number there, or that coefficient, and just one of the letters, any combination here. And one more, let's just say we can just do, I don't know, I guess I'm a little indecisive here. I'll just say something like 2z, right? But that's perfectly fine. Those are just 5 examples of some things that go into this monomial if you were to multiply. All right, let's go ahead and check out this next couple bit of problems. We're going to go and find the GCF and LCM for some given values here. Up to you what strategy you want to use. I'm going to use the ladder method. I just think it's one of the quicker ones if you know your facts pretty well. But prime factorizations are nice too. So 64 and 48, I think the first thing that comes to mind for me is going to be 8. 8 times 8 is 64, 8 times 6 is 48, and then I'm thinking here between these two we could put a 2. This goes in 4 times and 3 times. So the GCF here is just going to be the numbers on the side. So 8 times 2 here is going to be our GCF. That's going to be 16. And then for the LCM, you have a few different choices here. I think what I'm going to do is just multiply the diagonals here. So I'm going to just do 48 times 4. Again, you can choose to do 64 times 3 also, or you can multiply all the numbers on the outside. L, so 48 times 4 here. That's going to be 32, carry the 3. I think this is going to be 192. So I think the LCM here is going to be 192. But again, keep in mind, you could have also multiplied this diagonal as well, or you could have just multiplied everything along the outside here. Either way, you should end up with 192. All right, moving on to number 6. For number 6, we have a monomial, or 2 monomial expressions here. When you're going out and finding the GCF and LCM, you don't have to include the variable parts if you know how those are going to work, but feel free to write them in if you would like to. While 13 is prime, it is a factor of 65, so 65 breaks into 5 times 13, right? So 13 is a common factor here, it goes in 5 times and goes in 1 time over here. So we know right away actually that the GCF is going to have this 13 in common with both of them, right? 13. But what about the variable parts? Well, what do they both have in terms of A's? They look like they both have 1 A in common, and it looks like they both have 5 B's in common. So for the GCF, you just choose the lower exponent of each of those variable bases. So we can go ahead and just write it like this for the GCF. Now, as for the LCM, let's go ahead and just multiply. I think I'm just going to do 65 times 1. I think that's easier, right? But 13 times 5 is also 65, or if you multiply the outsides here, you're still going to get 65 for that coefficient, or again, that whole number in front of the letters. And then for the variable parts, you just pick the higher exponent of these. So the first time a squared and a meet is going to be at a squared. And then the first time this b to the 5th and b to the 8th meet is going to be at b to the 8th power. So again, you can just choose the higher exponents for each of those variable bases. All right, to take a look at number 7. For number 7, looks like we're back to whole numbers here, but we do have 3 of them this time. So let's see here. We have 35, 28, and 24. Now, if you're trying to find out first time 3 numbers meet, you have to be careful here. We do want to find out a number that goes into all of them if we can at first. And it looks like for 35 and 28, you can divide them both by 7, but 24 can't do that. I don't think any of them have anything all in common, actually. So I think the GCF here is just going to be 1, right? I can't think of anything that's going to go into all 3 numbers besides 1. So if that's the case, we know our GCF here is just going to be 1. All right, so there is no other number that went into all of them. But for the LCM, before you go ahead and try multiplying all these together, you want to see what goes into just 2 of them instead of all 3 of them now, right? So while 1's the GCF, let's keep looking for an LCM here. I think I'm just going to pick 7 that goes into 35 and 28. Again, that goes into both of them. So if we put 7 into those, it goes in 5 times and 4 times. This 24 at the end is just going to come on down, okay? Again, the 7's not part of the GCF because it wasn't in common for all of them, right? But at this point, I think what we can do is say, well, 5 and 4 have nothing in common. The 4 and 24 do. 4 goes into both of those evenly, right? So this 5 didn't really do anything there. It just kind of come on for the ride. 4 goes into 4 1 time. 4 goes into 24 6 times. All right, at this point, this 5 and 1 have nothing in common. The 1 and 6 don't have anything, and the 5 and 6, so they're all relatively prime. So when you're going to go ahead and find the LCM of these 3 numbers, we're going to go ahead and multiply each of these numbers on the outside. So 1 times 7 times 4 is 28, and on the bottom here, we have 5 times 1 times 6, which is 30. So I'm just going to go ahead and multiply 28 by 30 on the side here, and that should get us our least common multiple here. So let's see, that's gonna be 0 0, and then that's gonna be 24, carry the 2, and that's going to be 8. So adding these together, we're gonna get the first time they're gonna meet is gonna be at 840 for the numbers 35, 28, and 24. For number 8, we have these 2 monomial expressions. We have 42x squared y to the 4th and 28x to the 5th times y. Just like earlier, I'm going to go ahead and just look at the coefficients, this 42 and 28. What they have in common here is I'm going to go with a 7. I think that's probably a more common number for people to choose. I'll go with 6 and 4. Notice these are both even numbers, so we can do this process again. We have a common factor of 2, so we have a 3 and a 2 here. I think 3 and 2 are relatively prime, so I think we're going to be done factoring there. So the 7 and 2 on the side tell us that the greatest common factor is going to have a 14 as part of it. And then let's just look at the variable parts to figure out what they have in common. So this has 2 x's and this one has 5, so I think it's fair to say they both have 2 x's in common. And then if we look at the y's here, this one has 4 y's multiplied and just 1 y for the other one, so they both have 1 y as a factor, right? That's a common factor. For the least common multiple, let's just go ahead and 42 times 2, that's going to be 84. So I'm going to go ahead and write 84 is going to be the first time they meet in terms of their whole numbers or their coefficients. And then if you look at their variable parts here, this one has 2 x's and this one has 5 x's. So the first time they have something in common, xy's, is going to be x to the 5th power. And then in terms of the y's, we have y to the 4th and y to the 1st. So we're going to say y to the 4th power. So again, pick the higher exponents for the LCM in terms of the variable bases. And then for the GCF, pick the lower of the exponents for the variable bases. All right, so there you have their GCF and LCM for these two monomial expressions. All right. For 9 through 12, we're going to go ahead and see if we can rewrite each of these expressions as using the least common denominator or the LCM of the denominators and with using a single fraction bar here. All right, so let's see, we're going to add these two fractions, but notice they don't have the same denominator, so let's go ahead and take care of that. So let's see the first time that these two numbers meet, so we can use that least common denominator. So 45 and 36 looks like 9 is a common factor, so that's going to be 5 and 4 here. Now, in terms of the first time these two numbers meet, I think I'm just going to go ahead and multiply the outside numbers because I think that's a little bit easier to do. 9 times, let's see, 5 times 4 is 20. 20 times 9 is 180. So the least common denominator here is going to be 180. Right? So how do we get there? Well, 45 times 4 is going to be that 180. So I'm going to write times 4 times 4. And then over here, let's see, it's going to be 36 times 5. That's also 180. So it's 36 times 5. So if you rewrite these two fractions, 13 times 4 on top is going to be 52. So it's going to be 52 over this 180 plus, and then 11 times 5 is going to be 55. So we're looking at 55 over 180. So if you go ahead and add 52 and 55, since we have common denominators now, that's going to be 107. So we're looking at a final expression using a single fraction bar of 107 over 180. All right, for number 10, we have a couple mixed numbers here. We have 7 and 1/6 minus 2 and 5/9. We're going to make sure if we're going to subtract these rational numbers, we're going to make sure that we have common denominators first. So we have the 6 and the 9. Let's see, they meet here. They have a common factor of 3, so we have 2 and 3 left over. If you just go to multiply these outside numbers here, we're going to get that the first time they meet is going to be at 18. So hopefully that makes sense. To get to 18, it's going to be times 3 for the 6, so do it on top and bottom. And for 9, let's go ahead and multiply it by 2. So if we go ahead and rewrite these mixed numbers, we're going to have 7 and, let's see, 7 and 3/18. We're going to go ahead and subtract that. We have this 2 and 10/18. Okay, now we're going to go ahead and rewrite this just because taking away 10 from 3, we are going to have to borrow a little bit. So I'm going to rewrite the 7 and 3/18 as 6, and then move 18/18 over to the 3/18. That's going to be 21/18 here. All right, so I know it's a little weird to have kind of an improper fraction inside the mixed number, but it's just temporary while we are subtracting. And so if we go ahead and subtract the fractional parts and the whole number parts, 6 minus 2 is going to be 4 for the whole number, and then 21 minus 10 is going to be 11, so we're looking at 11/18 here. So this would be the difference between these two rational numbers. All right, for number 11 and 12, looks like we're going to be adding some monomials together, so rational monomial expressions. So let's see if we can figure out how to do that. So let's see the common denominators here first. I don't think we can simplify each of these rational expressions on their own. I don't see anything in common between the numerator and denominator, so it's always good to look for first, but I don't think we can here. So looking at the denominators, here we have these two different ones. Let's go and see the first time they're going to meet here. So if we go ahead and find the LCD, let's see. For the LCD, I think 10 and 8 are going to meet for the first time at 40, so that's going to be the first part of that. One of them has A's and the other one doesn't, so it needs all the A's and all the B's that they both have because that's the highest exponent of each variable base. So how are we going to get to this LCD? Well, for this first one, we're going to have to multiply this by 4, 10 times 4 to get 40. It already has the 3b's here, but doesn't have the 4a, so let's multiply by 4a to the 4th. And if you do that on bottom, let's also multiply it on top, 4a to the 4th power. For the other base here, to get to 40, 8's going to have to multiply by 5, and then it already has the a to the 4th power, so it needs the b to the 3rd power to get to that same denominator. Now if we do that on bottom, let's go ahead and multiply the top also by this 5b to the 3rd power. Okay, so what are these new fractions going to look like here? For the first fraction, 4 times 3 is going to be 12, so we're going to have 12, looks like a to the 10th power, right? Because we have 10 a's multiplied together in total. For the denominator, we're going to have that LCD of 40 a to the 4th, b to the 3rd power. And then we're going to go ahead and add on over here. It looks like we also have this 40 a to the 4th power, b to the 3rd power. But the numerator we're going to have is 7 times 5, which is 35. And then we have b squared times b cubed, which is going to be b to the 5th power. All right, at this point, you can see we do have these common denominators here, so we can rewrite this using a single fraction bar. Don't overthink the numerators. You can actually just for now write this 12a to the 10th power plus 35b to the 5th power. Just go ahead and write the sum of those since we're adding these two fractions together, and then just keep this 40a to the 4th power, b to the 3rd power in the denominator. So this would be our combined expression so that we only have one fraction bar. All right, for number 12, we have another example here, but this time we have a difference. So we're just going to put a minus sign in the numerator when we're done instead of a plus sign. Looks like for these denominators, we're going to go ahead and find out the first time they're going to meet. So that's going to be the LCM or the LCD in this case. I checked to see if we could simplify each rational expression on its own, each fraction, but I don't think we can in this case. So let's see, 9 and 12, I think they're going to meet at 36 for the first time, but feel free to check that. And then they don't have anything in common, so we need the highest exponent of each of these. So the highest of each is really just that x to the 4th and y to the 5th power. All right, so how are we going to get to this 36 x to the 4th, y to the 5th? Well, to get from 12 to 36, we're going to have to multiply it by 3. This already has 5 y's multiplied together, but doesn't have the x's, so it needs all 4 x's. So if we do that on bottom, let's go ahead and do that on top too. Multiply by 3x to the 4th power. Okay. For the 9x to the 4th power, 9 times 4 is going to be the 36. It already has the 4 x's multiplied together. It does need the y's. It needs all 5 of them. So let's go ahead and multiply by all 5 of these y's. Okay, so what are these new fractions on their own going to look like? Well, for each of them, they're going to have the LCD on the bottom. So it's going to be 36 x to the 4th, y to the 5th, and it's going to be minus this other fraction, but again, it's going to have the same denominator of 36 x to the 4th, y to the 5th, right? So those denominators are the same now. They're the least common denominator. But for the numerators, we're going to have 21, I think it's going to be x to the 7th power here. And then for the other fraction, I think we're going to have 32, and it looks like it's going to be y to the 7th power. Okay, so at this point, we should just be able to rewrite this as one fraction because we have common denominators. So this 36x to the 4th, y to the 5th, that's our least common denominator. So again, just keep this the same. It's just a lot of rewriting that. And then on the top, we have 21x to the 7th power minus this 32y to the 7th power. This would be our rational expression using just one fraction bar. Let's check out number 13 through 16, where we're going to be multiplying and dividing or finding the product or quotient. For number 13 here, let's go ahead and see. We're multiplying these two rational expressions, but we're going to need to make sure we rewrite them using just improper proper fractions first. So this 5 and 3/5, that's the same thing as 28 fifths. So we have 28 over 5 multiplied by this 9 over 14. Now, if you take a look at this, you can notice that 28 and 14 can both divide by 14. That's a greatest common factor. So you divide by 14, you get 1 and you get 2. And then if you go ahead and check for seeing if we can cancel anything else out, I don't think we can. I don't see any other common factors besides 1. So 2 times 9 is going to be 18. 5 times 1 is going to be 5. And then if we go ahead and turn this into a mixed number, 5 goes into 18 3 times. With 3 left over, right? So it's going to be 3 and 3/5. Okay. Moving on to number 14. 14, we're multiplying these monomial expressions here, these rational ones. I do think we can simplify each of these individually. So if you look at this first fraction, I think we can divide the top by a common factor. I think they have 3 a's on the top and the bottom. The 8 and 15 have nothing in common. So we can divide the top by a to the 3rd power and b to the 2nd power. I think we can divide this bottom by the same thing, right? So they both have 3 a's and 2 b's multiplied together. But I don't think they have anything else in common. So that's the GCF between the numerator and denominator. But let's go ahead and see. If we rewrite this fraction here, the 8 is going to stay on top. If we divided 3 a's out, there's going to be no more a's. And if we divided the 2 b's out, we should still have b to the 6th power. On the bottom, we still have this 15. All 3 a's got divided out and all the b's got divided out. So I think we're just going to have this 8b to the 6th power over 15. Let's go ahead and multiply this by, let's see what else we have here. I think this fraction can also be simplified. Let's go ahead and divide the top here. They both have, the 9 and 10 have nothing in common, but the a's, looks like there's 4 a's on top and bottom, and also there's 1 b on top and bottom. So I think we can divide these both by their GCF of a to the 4th power and multiplied by b. All right, so the 9 and 10 looks like nothing could be done with those. But if we divide 4 a's out on top, we're still left with a to the 4th power. And then it looks like if we divide 1b out, we're left with b squared. And then it looks like for the denominator, all a's kind of canceled out there, and then the b's also canceled out there. So it looks like we just are left with this 10 on the denominator. Okay. If you go ahead and check to see if we can do any cross canceling, I think we can, right? I think the 9 and the 15 can both divide by 3. So we're going to end up with 3 and 5 if you divide them both by 3. And then for the 8 and 10, I think you can divide those both by 2. So we'll end up with 5 here and 4 here. I think that's it in terms of their common factors that we can simplify by. And so if we multiply the coefficients here, 3 and 4, that's going to be 12. And then it looks like we have a to the 4th power on top here. So let's go ahead and write times a to the 4th power. And then we also have 6 b's multiplied together by 2 more b's. That's going to be a total of 8 b's multiplied together. And this is all over what? It looks like we just have 5 times 5, which is going to be 25. So this would be our final product or simplified monomial expression. All right, now that we went ahead and found a couple products, let's go ahead and practice finding a couple quotients. For number 15, looks like we're dividing some mixed numbers here. So we can rewrite the equivalent of 6 2/3 as an improper fraction. That's going to be 20 over 3 divided by, and then 4 2/7 as an improper fraction is going to be 30 over 7. All right. Now, if we have this division problem, let's go ahead and rewrite it as a multiplication problem by multiplying that first fraction by the reciprocal of the second fraction. So it's going to be multiplied by 7 over 30 here. All right. Now you could multiply these and then simplify after, but I think I'm going to divide these both by 10, the top and the bottom. So we get 2 and 3. So we have much smaller numbers here. And then I think that's it in terms of simplifying. So 2 times 7 is going to be 14. And then 3 times 3 is going to be 9. And then so I think what we can do is rewrite this as a mixed number. So 9 goes into 14 one time with 5 left over. So we can write our final quotient here as 1 and 5/9. Okay. For number 16, looks like we have another monomial expression here. So we can rewrite this as a multiplication problem. But I think what we're going to do first here is actually simplify each of these fractions or expressions on their own. So just looking at the numerator and denominator for the first rational expression, 21 and 16 have nothing in common besides 1. However, for the x's, they both have 1 x in common, and they both have 2 y's multiplied in common as well. So let's go ahead and divide the top and bottom by xy squared. That's their GCF for the numerator and denominator. And then for the second fraction here, for 14 and 8, they both can divide by 2, right? That's a common factor. They both have 4 x's in common, so x to the 4th power, and they both have 1 y in common. So we're going to go ahead and just divide both of these by their GCF of 2x to the 4th y. Rewriting each of these expressions with using a more simplified version here, let's go ahead and see. We have 21, and then we have x to the 3rd power. And then we're going to have no more y's in the numerator. In the denominator, the 16 is going to stay here. If we get rid of the x, there's no more x's, but we still have 3 y's left in the denominator after you divide out 2 of those y's. We're going to divide this by the second expression here. So 14 divided by 2, we're left with a 7 on top. Let's see, all 4 x's got divided out and 1 y gets divided out. So we're still left with 2 more y's after you divide y cubed by y. You still have y squared. And in the denominator, 8 divided by 2 is going to be 4. And then let's see, 4 of the x's are being divided out. So we still have x. And I think the 1 y got divided out. So we have no more y's. Let's go ahead and rewrite this as a multiplication problem. So we have 21x to the third power over this 16y to the third power. And we can go ahead and multiply by the reciprocal of the second expression. So we're going to put the 4x in the numerator and this 7y to the second power in the denominator. Now, before we go ahead and just multiply the tops and the bottoms, let's see if we can cross cancel a little bit. I think 4 and 16, you can divide those both by 4. And if you do so, you get 1 and 4. And if you divide 21 and 7 both by 7, you're going to get 1 and you're going to get 3 here. All right, so let's go ahead and see if we actually multiply these together. For the coefficients on top, 3 times 1 is just going to be 3. And if you multiply these 3 x's by 1 more x, we're looking at x to the 4th power, a total of 4 x's in the top. On the bottom, we have 4 times 1. That's going to be 4. And then for the y bases, we have 3 y's multiplied together by 2 more y's. That's going to be y to the 5th power. All right. I don't think there's anything else that can be simplified here, so I think this will be our final quotient, or the answer to the division problem that we started with. For number 17 and 18, let's go ahead and see if we can find the average of each of these following expressions or numbers. Average, keep in mind, we're just going to be adding up all the values that we have and then dividing by the number of numbers that we have. So in number 17, looks like we have 4 different values. So let's go ahead and find the sum of these values, then divide that by 4. All right, so again, I'm going to rewrite this all out. So to find the average of these, I'm going to write an expression for this. So I'm going to turn these all into improper fractions as well as I go. So negative 4 2/3 is the same thing as negative 14 over 3 plus, let's see, 3.5 is just going to be 7 over 2. The 6 over here is just going to be 6 over 1. And then the 5/6 is already a proper fraction here. So I'm just going to rewrite it like this. So we're going to find the sum of all of these, and then we're going to divide it by 4 afterwards, or you could put a fraction bar and divide it by 4. All right, so at this point, you can look at all the denominators here, 3, 2, 1, and 6. And the first time they meet, it's not too bad. It looks like they're all going to meet at 6 here, right? So how do you make these all 6? Well, you can just do times 2 times 2. You can do times 3 times 3. You can do times 6 times 6. And then you can leave this alone or write times 1 times 1. And so if you go ahead and rewrite this here, looks like we're going to have negative 28 plus, what do we have? 7 times 3 is 21. Plus 6 times 6 is 36, plus 5 times 1 is going to be 5. So we go ahead and add all those numerators together once they're all over the same denominator of 6, and then divide by 4 here. All right, now negative 28 plus this 21 is going to be negative 7. Negative 7 plus 36 is going to be 29. 29 plus 5 is going to be 34. So we're really looking at here of 34 over 6. And we're going to divide this by 4. But when you divide by 4, we're really going to say it's multiplied by 4 over 1, right? So rewriting this as a multiplication problem, this is going to be 34 over 6 times 1 over 4. Then we can go ahead and, before we multiply, cross cancel. We can divide these both by 2, so this will be 17 and 2. And then so on the top, we have 17 times 1, which is going to be 17. On the bottom, 6 times 2 is going to be 12. So we're looking at a final answer here where the average of these 4 fractions is going to be 1 and 5/12. For number 18, let's go ahead and find the average of these 4 different rational expressions or rational numbers here. So let's see. I'm going to rewrite these all using an improper or proper fraction as well. So negative 5, I'm going to write as negative 5 over 1. Plus this negative 5/8, that one's fine, negative 5 over 8, just leave it alone. Then plus, let's see, this is going to be 12 plus 3, that's going to be 15 over 4. And then this 2.5 is just the same thing as 5 over 2. So we're going to add up these to find the sum, and then we're going to divide that by 4 when we're done to find the average, okay? We need some common denominators here. If you look and see, we have 1, 8, 4, and 2, so it's not too bad. I think they're all going to meet at 8 for the first time. So for this first fractions, go ahead and multiply by 8 and 8. For the second one, we can do times 1 times 1. The third one we could do times 2 over 2, and the last one do times 4 over 4. All right, so if we go ahead and rewrite this, we're going to have everything be over 8. So it's going to be negative 5 times 8 is negative 40, plus we have negative 5 times 1, it's going to be negative 5, plus 15 times 2 is going to be 30, plus 5 times 4 is going to be 20. So these would be all the numerators, and again, I'm just rewriting these all over 8 since they're all going to have common denominators of 8, and then let's divide this by 4 afterwards. All right, so let's see here. Negative 40 plus negative 5 is negative 45, plus 30 is negative 15. Negative 15 plus 20 is going to be 5. So we're looking at 5 over 8 divided by 4. 4 is just 4 over 1. So we can go ahead and rewrite this as a multiplication problem. Say this is 5/8 multiplied by a quarter. And we can't cross cancel anything, so it's just going to be 5 over 32. And I'm just going to go ahead and write that over here just to make it more clear. All right, last two problems here. We have 19 and 20. We're going to determine the missing dimension for each polygon given here. So for number 19, we have a rectangle. It has a length of 8 3/4 inches and an area of 23 1/3 square inches. We're going to write and solve an equation to determine the width of this rectangle. All right, so hopefully you're imagining something that looks like this, where we have area of a rectangle, and then we have a length going across the bottom here maybe, and then the width here, we don't know the width, that's going to be this missing dimension. So hopefully for rectangles, if you multiply the length and the width together, we do get the area, right? So hopefully we can rearrange that equation and say the area divided by the length should get us the width here. So we can write an initial equation and just say that the width would be equal to the area divided by whatever the length is going to be. And in this case, we can go ahead and start solving for that by plugging in and saying the capital A, or the area, is going to be 23 1/3 divided by this 8 3/4. Okay. Now, could we rewrite these mixed numbers? Absolutely. So 23 1/3 is the same thing as 69 plus 1 is 70. So it's going to be 70 over 3 divided by this, what's 8 3/4 as a mixed number? That's going to be 32 plus 3 is 35. So we're looking at 35 over 4. Okay. Now, how do you rewrite this as a multiplication problem again? Well, we can say that the width here would be equal to 70 over the 3 multiplied by the reciprocal of 35 over 4, which is going to be 4 over 35. All right, now it's a multiplication problem. You could just go in and multiply the tops and the bottoms and then simplify, but I think we can go ahead and cross cancel. 35 times 2 is exactly 70, so if we divide these both by their GCF of 35, we're going to get 1 and we're going to get 2, which makes these numbers much nicer. And then on top here, 4 times 2 is going to be 8. On the bottom, 3 times 1 is going to be 3. So actually the width here is going to be 2 2/3. What kind of units do we have? Well, I'm just going to write 2 2/3 over here for now. But then to kind of summarize this, we can say that the width of this rectangle must be 2 2/3 inches long. If you wanted to go ahead and check this, what you could do is you could make the argument that you could take this 8 3/4 and multiply it by this 2 2/3, and you should be able to verify that it does equal this 23 1/3. So that'd be a great way to check to see if your division was correct, or to see if the width was correct for this rectangle. All right, for this last example, let's go ahead and take a look at number 20. We have a triangle that has a height of 5 1/3 centimeters and an area of 40 square centimeters. We're going to write and solve an equation to determine the base of this triangle. All right, so here's a hypothetical triangle that I just kind of sketched so we can kind of see what's going on here. We know the area, or the amount of space inside the triangle, is 40 square centimeters. We also know the height of this is 5 1/3 centimeters tall. The question is what's the base, or how far across is this triangle going in the horizontal direction here, right? You didn't have to draw the triangle like this. This is just what I was imagining, and that's perfectly fine here. So how do you find the area of a triangle? We need a formula here. Well, the area of a triangle is, one way you could write the formula is 1/2 multiplied by the base multiplied by the height, right? That's one way you could write this formula out. If we're going to be looking for this base here, then what we have to do is think about how could you rearrange some of this formula here, right? So if you go ahead and if you have to take the base and height and multiply it together, then take half of it to get the area, then what if you were trying to find the base? Well, to find the base, you would have to go ahead and multiply this area by 2, right? Because you have this 1/2 you're going to divide by at some point. And then you also have to divide by the height here. So one way you could rearrange this formula is the base would also be known as 2 multiplied by the area divided by whatever the height is going to be. All right, so if you want to check this, feel free to do so with just like maybe a triangle with easier numbers and see if this makes sense. But this would help you find out that missing dimension. Okay, so let's go ahead and see if we can find the base here. All right, so the base is going to be 2 multiplied by the area. The area we know is going to be 40, and then divide by the height here. The height here is going to be 5 1/3. Okay, so let's go ahead and rewrite this so that we have some fractions throughout this whole expression on the right side here. So we have 2 as 2 over 1, we have 40 as 40 over 1, and then we're going to divide this by this 5 1/3, which is really just 16/3. Okay, we can also rewrite this as 2 over 1 multiplied by 40 over 1 multiplied by 3 over 16 if we rewrite that division as a multiplication problem. Right. At this point, you can also simplify before we multiply. So 40 and 16, you can divide them both by 8. So we're going to be left with 5, and we're going to be left with 2 here. But then notice you can actually cross cancel a second time. This 2 and 2 can cross cancel to make 1 and 1. Right, so that actually came out pretty nice here. So in the denominator, we just have 1s all the way across the bottom. So 1 times 1 times 1 is 1. And on top, we have 1 times 5 times 3, which is 15. So 15 over 1 is just 15. So the base of this triangle must be 15 centimeters long. So let's go ahead and put 15 right over here. And if you want to check this, what you can do is take this 15, right, and multiply it by this 5 1/3. You're going to see if you multiply 15 times 5 1/3, you're going to get 80. And if you take that 80 and divide it by 2, you do get this 40. That is the area here. So again, this formula might look a little bit strange at first, but it's really just a rearranged version of this one over here. And it's up to you kind of how you want to think that through. But keep in mind that we're dealing with triangles. After you multiply the base and the height together, you have to divide by 2 to get the area. So it kind of makes sense. You should double the area, then divide it by the height to figure out that the base here, what that's going to be. So putting this all together and summarizing, the base of this triangle must be 15 centimeters long. All right, so that just about wraps up this video on 20 different practice problems where we practiced applying our understanding of factors, multiples, and dealing with some operations of rational expressions. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or a friend who might also find it helpful. And as always, keep up the great work that you're already doing.